All right, well, here's a problem. So start by copying this problem onto a piece of paper. And then when you've copied it onto your piece of paper, you can turn on your screen sharing and show how you would show me how you would solve this problem on your screen. Let's get a prediction before we go into the math. What could you predict about your answer here?
So if this is lower, this is going to be higher. So I would predict that this is going to be around 10 to the negative 11.
Okay, so do you predict an acidic or a basic solution?
I predict a basic solution
With high or low proton concentration?
with very low proton concentration.
Okay, now I'm not sure if that matches the arrows that you drew.
Oh. It's going to be a lot bigger than the negative 7th. Oh.
So is this solution acidic or basic?
That is going to be a basic solution.
We can see that without doing any calculations because the amount of hydroxide is around 10 to the negative 3. And 10 to the negative 3 is much bigger than 10 to the negative 7. Okay, so now let's proceed with solving the problem.
I have 2.7 times 10 to the negative 12.
Okay, good. Let's go ahead and finish writing out our answer then on your screen. Okay, so that's important to include the units. Without the units, the answer isn't correct. Does that match our prediction?
Yes.
Yeah.
Yeah.
That's a small number, so that confirms that this is a basic, not a acidic solution. Let's see. Okay, so I've turned my screen on now. Let's go back to my screen. That's correct. So that's the type of problem that we worked on last time. So that's good that you remember how to do that. Last time we were working on logarithms. There were one or two topics for logarithms I realized we didn't get to that we are also going to need. For example, we didn't talk about this last time, so you may not know this, but do you happen to remember from high school what's another way to write this expression? This is not related to what we went over last time, but do you remember what another way to rewrite this is?
No.
So it turns out that the log of a product is the sum of the logs. That's a fact about logarithms. This is a fact about logarithms.
Mm-hmm.
Okay, so we'll just memorize that fact. So how could you rewrite this expression?
Log x plus log y.
That's right. Good. All right, the next topic to discuss is P. What does it mean to take the P of something? So when we take the P of something, that actually has a particular meaning in chemistry. Let's say we were taking the P of something X, for example. This means the negative log of X. So what does P mean? P basically means negative log. When we're taking the P of an expression, that just means we're taking the negative log of an expression. So this is a math trick that's useful in chemistry.
Okay.
For example, do you know or can you now figure out what does pH mean? How would you calculate the pH?
Negative log base of hydrogen.
Could you repeat that? I didn't hear you.
Negative log of hydrogen, or negative log. I heard negative log base of hydrogen before.
I'm not quite getting. You said negative log base of hydrogen?
Yeah, I don't know if that's correct. That's what
I don't understand what you mean by base of hydrogen.
I didn't either. And I
Okay.
Yeah.
Okay, looks like we need to clarify that a little bit. Now, for one thing, let's go back to what P of X means. What does it mean? What does P of X mean? It means the negative log of X. What do you think is the base of this log?
10.
10. How do you know? Well, we discussed this last time. If you're not told the base, you should assume the base is 10. So we could also say this is negative log base 10 of X. We don't actually have to write the 10 though, because base 10 logs are the only ones that we're working with. Now notice you wouldn't say this is the negative log base of X. That just is meaningless. It doesn't mean anything to say this is the negative log base of X. It's the negative log of X. If you want to mention the base, you could say it's the negative log base 10 of X. But we really don't have to mention the base because it's taken for granted that the base is 10 when we're working in biochemistry. All right, well, what I was hoping that you would do here is apply the rule that we just talked about. So if the P of X is the negative log of X, then the P of H should be the negative log of H. You were on the right track, but you were saying something weird. You were saying the negative log base of H. I'm not quite sure what that meant. If you wanted to, you could say it's the negative log base 10 of H, but it's simpler not to mention that. Now, we have to be a little bit more specific here, because what does the H stand for? It's kind of an abbreviation. What this really means is the negative log of this. What does this mean? How would you read this expression aloud?
Negative log of the concentration of protons.
That's right. So that's what pH is. I'm sure that you've heard this concept of pH before in some of your courses, but perhaps you weren't quite clear about exactly what it meant. So now we know what it means. It's the negative log of the proton concentration. It would probably be better if it was called P bracket H plus. It would be a better symbol to call it P bracket H plus, but the chemists got lazy and they just call it pH. But the H here really stands for concentration of H plus. All right, you have that in your notes?
Yes.
So to review, how do you calculate pH?
It's the negative log of the concentration of protons.
That's right. One thing we might wonder then is, what are the units for pH? What are the units for pH? Well, it turns out that that logarithms don't have units. That's a good thing to know. Logarithms don't have units. And since pH is the logarithm of something, it doesn't have units either. We need to know the units for concepts, but we also need to know the concepts with no units. So pH has no units. Now here's another symbol that we haven't talked about, but you might have seen in chemistry before. Let's try to figure out, what does this mean? How would you calculate the POH?
It's the negative log of the concentration of hydroxide ions.
That's correct. Because P is the negative log of something. Very good. What are the units for POH?
No units.
How do you know? Because it's a logarithm. Okay, so that's an important concept. Okay, so let's try this problem. Copy this onto your paper and then turn on your screen so we can try this problem on your screen.
I have 2.24.
Okay, what are the units on that answer?
There are no units.
Okay, that's the correct way to do that, basically. Now, I noticed you used brackets there. What do the brackets mean?
That would make no sense, actually. Because it means the concentration of.
Right. So you could write it like that, or since it's kind of a long number, it's probably better to put that in parentheses to show that we're taking that whole logarithm. So I think, as you might be remembering, that's a topic that we discussed in our previous session. A common mistake people make is to write the numbers in brackets. But as we talked about, that doesn't make sense. The brackets mean the concentration of. So there has to be the name of some ion or species, not a number in brackets. Okay. Also, do you see how you could kind of estimate this in your head? The pH is the negative log, but logarithms we saw last time are the exponent on the 10. So the pH is the negative of the exponent on the 10, or in this case it would be close to the negative of the exponent because there's also a coefficient. So we could have predicted from the start that the pH would be close to what?
We could predict that the pH is
Without using your calculator, we could already have predicted that the pH would be close to what integer?
I'm not understanding.
So my point was, do you remember we've seen that we can actually estimate logarithms without using a calculator? Because we know that the logarithm is basically referring to the power of 10.
Right.
Or in this case, because there's a coefficient, it would just be close to the power of 10. So in this case, the power of 10, what was the power of the 10?
5.7 times 10 to the negative third.
Maybe you're not understanding what I mean by power. Do you know what the power is?
Negative 3.
Yeah, that's right. The 5.7 is what we would call a coefficient. The 5.7 is the coefficient. The power is the negative 3. Well, logarithms refer to the power. So we could estimate that the logarithm would be close to negative 3. Since we're taking the negative logarithm, the answer should be close to 3. So the point is the pH is the negative logarithm. Logarithms are exponents, so the pH is the negative of the exponent. So in this case, we would expect the pH to be close to 3. And that's how it turned out. Our answer was 2.24, which is not that far from 3. So that's good.
Because of the exponent, the answer is going to be close to it? Like if it was like, let's say, to the negative fifth, the answer would be somewhere around 5.
That's correct. Yes. That's just a review of what we went over last time. We already were seeing last time how to approximate logarithms by saying the logarithm is always going to be close to the power of 10. After all, if it was just exactly 10 to the negative 3, if the proton concentration was exactly 10 to the negative 3, the logarithm would be exactly negative 3. So if the proton concentration is close to 10 to the negative 3, then the logarithm is close to negative 3. And because the pH is the negative of the logarithm, the pH will be the negative of the exponent. That's just a good way to double check yourself to make sure you haven't made a calculator error, for example. Okay, so that gives us a little bit more of a feel for this. Now, do you see why it's useful, why pH is useful? Do you see why pH is useful? Was this proton concentration a big number or a small number?
The proton concentration is a big number.
What number is it? Oh, why did you say big?
Compared to the -7.
Okay, that's not what I was going for, but that's a reasonable answer. Yeah, compared to 10 to the -7, it's big. My point, though, is just in the scheme of numbers in general, 5.7 times 10 to the -3 is a pretty small fraction. My point is that 5.7 times 10 to the -3 is a pretty small fraction. My point is that it's so small, you kind of have to use scientific notation to write it clearly. So do you see the advantage of using the pH scale? It turns a very small number into an ordinary sized number. Instead of having to use this tiny number, 5.7 times 10 to the -3, which is equal to 0.0057, we can just use an ordinary size number, 2.24. So my point is that pH is useful because it allows us to work with ordinary sized numbers, ordinary integers, rather than tiny fractions, because it just focuses on the exponent. Okay, all right, in any case, now we saw here how to take the pH. Let's see. The next few minutes of the tutoring session didn't get recorded, so I'm going to re-record that material now without the student for the benefit of people who may be watching this video on YouTube. So let's see, the next topic that we discussed in the tutoring session. So what I'll do here is I'm going to pose a series of questions to you, the person who is watching this video. I hope that after each question you'll pause the video and give it some thought before proceeding. So my first question is, what is the chemical equation for water autoionization? What is the chemical equation for water autoionization? I hope you paused the video and came up with an answer. The answer is this. As I think we've already covered earlier in these tutoring sessions, this is the chemical equation for water autoionization. So here's the next question. What is the mathematical equation for water autoionization? What is the mathematical equation for water autoionization? Again, I hope you paused the video and came up with an answer. Well, we just used the idea of an equilibrium constant. Remember that the equilibrium constant for this reaction is the Kw. And then equilibrium constants consist of the products on top Usually we put the starting material's concentration on the bottom. But remember that when you have a pure liquid, you leave that out. We'll leave this out because it's a pure liquid, or you could think of that as the number 1 on the bottom. So in this case, the mathematical expression becomes this. So this is the mathematical equation for the water autoionization reaction. This is the mathematical equation for the water autoionization reaction. This equation is always true. All right, here's the next question. What can we plug in for Kw? What can we plug in for Kw? As we've learned, Kw is 10 to the -14. All right, now what I'm going to do next, we're going to do a little math. All right, so buckle your seatbelt. Here comes a little math. The first thing we're going to do is we're going to take the logarithm of both sides of the equation. So try that. Try to take very small steps. So just write down, what would this look like if we took the logarithm of both sides? What would this look like if you took the logarithm of both sides? Well, I hope you wrote down something like this. I hope you put in these parentheses to show we're taking the log of the whole left-hand side. Well, we know this is legal because of the golden rule of algebra. The golden rule of algebra is that you can do anything you like to the left side of the equation as long as you do the same thing to the right side of the equation. So it's perfectly okay to take the logarithm of the left side of the equation as long as we also take the logarithm of the right side of the equation. All right, now we need some more math. The next math is let's simplify this equation. How could we simplify the left side? I hope you'll pause the video and think about how you could simplify the left side. Well, remember we went over the rules for logarithm earlier in this session, I believe. The log of a product is the sum of the logs. We saw that rule earlier in this tutoring session. The log of a product is the sum of the logs. So I hope you came up with that for the left. And now pause the video and try to simplify the right-hand side. Simplify the right-hand side. Using the techniques we went over earlier, this is negative 14. We went over techniques. You could do this on your calculator, but I hope that you've learned from the video how to evaluate simple logs like this without your calculator. Okay, so we know that this is negative 14. Let's see. Now I want to multiply both sides by negative 1. So again, try writing down what you would get if you multiply both sides by negative 1. I hope you got this. Again, I hope that you remembered to put in parentheses here. Oh, I almost forgot. I hope you remembered to put in parentheses here because we need to multiply the entire left side by negative 1. Again, how do I know that's legal? Because of the golden rule of algebra. You can do anything you like to the left side of the equation as long as you do the same thing to the right side of the equation. So it's okay to multiply the left side by negative 1 as long as we also multiply the right side by negative 1. Why am I doing all this stuff? Why am I taking logs and taking negative 1? Well, just trust me for a couple more minutes and you'll see why. So it turns out that we'll get something interesting if we follow this path. So let's see what happens if we follow along this path. So next, please pause the video and rewrite the left side of this equation. How could you simplify the left side of this equation? Well, I hope you used the distributive rule. The distributive rule can simplify this left side. And how could you simplify the right side? Well, negative 1 times negative 14 is positive 14. Of course, I could write this as just subtract log hydroxide, but it turns out to be a little more convenient to write it like this. Now again, how can we rewrite the left-hand side of this equation? Can you see any way to rewrite the left side of this equation? I'll give you a hint. How can you rewrite this term? What is this term? Pause the video. Can you see any way to rewrite this term? Well, I hope you remembered that negative log of h is the pH, right? We saw earlier that the negative log of h plus is the pH. So now how could we simplify this term? Well, negative log of hydroxide is POH. Maybe now you can see why I multiplied by negative 1. We multiplied by negative 1 here because I wanted to get these into a form that looked like pH and POH. Okay, anyway, now we finished the mathematical argument and we've come up with a useful equation. pH plus POH equals 14. Hopefully most of you are already familiar with this equation. Hopefully most of you have already seen in previous chemistry courses that the pH plus the POH adds up to 14. But I think it's a good exercise to be able to have seen this proof. You're probably not going to be asked to prove this on a test. You probably won't be asked to prove this on a test. But I think it's good to see. Here we have our two key equations. So here's two equations that you do need to have memorized. So like I said, you probably are not going to be tested on this proof, but you definitely will be tested on this idea and this idea. You definitely need to know this equation and this equation. You need to know that if you multiply the concentrations, they equal 10 to the negative 14. And you need to know that if you add the pH and the pOH, they add up to 14. So that's what you need to know. Like I said, you won't be tested on this proof, but I thought it was useful to show it just so you can see these two equations are two sides of the same coin. I just wanted to convince you that this idea here is not a new idea. It's just another way of expressing this idea. I just wanted to convince you here that this idea is not something new, it's just another way of expressing the idea we already had up here. So I just wanted to show you this proof to give you a little practice with logs and also so that you could see these two equations are two sides of the same coin. But what you need to know for the test is you just need to know these two equations that I put in boxes, and you need to have them memorized and know how to use them to solve problems. We'll go over that more later in this video. One thing I like about this little proof here is hopefully it shows you that this area of chemistry, we're often talking about two different levels. There's two different levels at which we can analyze acid-base problems. Two different levels at which we can analyze acid-base levels. There's the concentration level, and there's the P level. These don't have very good names, but we could call one of them the brackets level, or the concentration level. And we can call the other one the P level. These are two different levels at which we can talk about acid-base problems. What type of number do we usually use for concentrations in acid-base problems in chemistry and biochemistry? What type of number do we usually use here? What type of number? It's kind of a vague question. Do we use ordinary sized numbers, big numbers, small numbers? Well, have you noticed that we usually use very small numbers for concentrations? In your biochemistry class, you're usually going to use quite small numbers for concentrations. For example, you might use a number like, say, 3 times 10 to the negative 4, which is a pretty small number. This is a very small fraction. So we usually use pretty small fractions. You don't have to. You sometimes use ordinary sized numbers. Oh, and what would be the units for this level? That's very important. What would be the units for this level? I hope you said molar. Or actually, a lot of the time in biochemistry we use millimolar. Unfortunately, when I was working with the student, I gave most of the examples in terms of molar. I realize now I should have emphasized in biochemistry a lot of the problems are about millimolars. So I hope you understand what the concept of millimolars is. So sometimes in biochemistry you use molars. Oftentimes in biochemistry we use this concept of millimolars. Okay. Anyway, here, the point is here we have a pretty small number. Maybe I'll make it a little bit smaller. No. Okay. Now, what type of numbers do we use at this level? What type of number would we use at the P level? What type of numbers do we usually use? Huge numbers, ordinary sized numbers, or tiny numbers? Well, I hope that you know from your past experience, we usually use ordinary sized numbers here. We usually use numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Usually numbers around that range. In fact, if this is the concentration here of H+, if this was an H+ concentration, what would be the pH? Pause the video and work that out. If this was the H+ concentration, what would be the pH? Well, the pH would be the negative log of 3 times 10 to the negative fifth. Is that what it was going to do? Okay. 3 times 10 to the negative fifth. So that would come out to be approximately 4.5 if this was the H+. Do you see how this is a tiny number and this is an ordinary size number? So I'm trying to make the point that we often use tiny numbers at the concentration level and ordinary size numbers at the P level. That's the whole point of taking the P of something. The whole point here is that a lot of the concentrations we work with in biochemistry are very small numbers. And the chemists just kind of get tired of working with such small numbers, so they take the P of the number so they can work with a more ordinary sized number. Do you see that these two numbers mean the same exact thing? If the H+ concentration is 3 times 10 to the negative fifth molar, that is the same thing as saying the pH is 4.5. If the pH is 4.5, that just means that the H+ concentration is 3 times 10 to the negative fifth molar. It's just describing the same thing at two different levels. Why would we want to describe it at this level? Well, the advantage of this level is that we get to use ordinary size numbers and we don't need scientific notation. Okay, so the chemists use this p level so that they can work with more ordinary, so that they can take tiny numbers and turn them into ordinary size numbers that don't need scientific notation. All right, so I wanted to emphasize anytime you're doing an acid-base problem in this chapter, this part of your course, you should try to make sure that you know, am I working at the brackets level or am I working at the p level? One of the biggest mistakes people make is they get confused between these two levels. For example, a lot of the time the question might be about the p level, but the student might be accidentally thinking about concentrations instead. Or maybe the question might be asking for a concentration and the student might accidentally be thinking about the p level. So just keep in mind there's two different levels that we can be working on these problems, and you always have to be conscious about what level you're working at. What level is this equation? What level is this equation? Well, this equation is at the brackets level, right? This is an equation you would use if you have concentrations at the brackets level. What level is this equation? Well, this equation is at the p level, right? Remember how I said that this proof shows us that these two equations are two sides of the same coin? These two equations are two sides of the same coin. It's just that here's the equation that explains the relationship between the concentrations at the concentration level, and here's the equation that explains the relationship between the p's at the p level. But they're two sides of the same coin. Okay. I hope those ideas are making sense. Maybe as you do more problems, they'll start to make more sense. So to review, you need to learn this equation for the brackets level and this equation for the p level. You should always keep in mind whether you're working at the brackets level or at the p level. We usually use tiny numbers in scientific notation at the concentration level in molars, and we usually use ordinary size numbers with no units at the p level. And these two equations, as we saw from this proof, are just two sides of the same coin. They're just looking at the same phenomena at two different levels. So let me give you one more illustration of what I mean by these two different levels. Do you remember the problem that we were just working on a little bit earlier in the video? Remember, I think I gave you, let's see, I gave the student this problem. I gave the student this problem. Here's the problem we already did. How does this tie into the levels? How does this question tie into the levels? Well, the point is the problem gave us information at the concentration level. Oops, I should have written it like this. The problem gave us information at the concentration level, and we had to change that into information at the p level. So this particular problem here could be symbolized like this. We started at the brackets level, and then we had to move to the p level. That's how you can think of a problem like that. There are some problems where you just move from one thing at the brackets level to another thing at the brackets level. There are some problems where you move from one thing at the p level to another thing at the p level. There's some problems where you start at the brackets level and you have to move down to the p level. And there's some problems where you start at the p level and you have to move up to the brackets level. So that's 4 different types of problems that you might see. And it helps to think in terms of these levels so you can see what type of problem you're working on. Remember that the answer to this question was this. So notice, as expected, we started with a tiny number that had to be written in scientific notation at the brackets level, and then we ended up with an ordinary size number with no units at the p level. The nice thing about working at the p level is we don't need to use this scientific notation anymore. It changes tiny numbers into ordinary size numbers. So as we continue working through the further problems, in this video, I hope you'll keep asking yourself whether each number is at the brackets level or the p level. And I hope you'll keep asking yourself about whether the question is asking about the brackets level or the p level. All right, here's a problem. Please pause the video and try working this problem out. I hope you gave that a shot. At this point in the tutoring session, the recording software started working again. So I will now return you to the previously scheduled program.
$7.2.
Okay, good. So, good. So you use that new equation that we had just worked out. That's right. Good. I'll go back to my screen. Okay, now let's try this problem.
Okay.
Let's see. Okay, that's correct. That's good. Now, something I think that could make this simpler is rather than putting both equations together, it would probably be simpler and lead to fewer mistakes if you first just calculated the POH. You could have just started by calculating the POH. And then you could just subtract that from 14. Then you could write, instead of writing pH plus negative log 5.8 times 10 to the negative fifth equals 14, you could have written that pH plus POH equals 14. It would just make your algebra a little bit simpler. But the way that you did it is correct as well, and you got the correct answer. All right. Do you remember last time we talked about what, say, a neutral solution was like? What did we say was the definition of it? What's the proton concentration in a neutral solution?
10 to the negative 7.
Remember that we always have to give units on any answer.
Molar.
And what's the hydroxide concentration in the neutral solution?
10 to the negative 7 molar.
So what's the definition of a neutral solution? The definition is a solution where the proton concentration is the same as the hydroxide concentration. Okay, good.
Wait, would that be true then if it was 10 to the, let's say the concentration of protons was 10 to the negative 10th, and then the hydroxide would be 10 to the negative 10th? That'd be a neutral solution?
That would be a neutral solution. However, that's not going to come up because remember that we also know that these two numbers have to multiply to equal 10 to the negative 14.
Okay.
Since they have to multiply to equal 10 to the negative 14, this is the only way they can be equal. That's how we know. So the definition of a neutral solution, do you remember we worked on this last time as well? The definition of a neutral solution is when the proton concentration equals the hydroxide concentration. Well, then if you remember what we did last time, we said that we could use x for both of these then, and then you can solve for x and find that x here has to be 10 to the negative 7. So we didn't just pull this number 10 to the negative 7 out of our hat. We picked out this number because this is the only way that they could be equal and multiply to be 10 to the negative 14. Now, remember this is the kW. kW is different at different temperatures. Remember, this is the kW at room temperature. If you were at a different temperature, the kW would be different, and then these concentrations could be different in a neutral solution. So if you change to a different temperature where the kW is 10 to the negative 20, well, then a neutral solution would have proton concentration 10 to the negative 10 and hydroxide 10 to the negative 10. In any case, in the body's not exactly at room temperature, but it's close enough that the kW is pretty close to 10 to the negative 14. So at physiological temperatures, this is not going to come up. At physiological temperatures, neutral is about 10 to the negative 7 for both. Okay, so that was a good question. Let's see. So what would be an acidic solution?
When the proton concentration is higher than the hydroxide concentration.
Excellent. That's the general definition. But what, in particular, the the proton concentration would be bigger than what number in an acidic solution?
10 to the negative 7.
Right, assuming that we're close enough to room temperature or physiological temperature. Okay, good. And what could you say about the hydroxide concentration in an acidic solution?
Be less than 10 to the negative 7th.
Molar. Okay. Now then, what about a basic solution? What can we say about that?
The proton concentration would be less than 10 to the negative 7th.
Molar.
Molar. The hydroxide ion concentration would be greater than 10 to the negative 7th molar.
Good. Now, the general definition of a basic solution is when hydroxide concentration is bigger than proton concentration. But that would mean the hydroxide is bigger than 10 to the negative 7 and proton is less than 10 to the negative 7. Now, remember that we said that there's two different levels to analyze these problems. There's the concentration level and there's the P level. So this table so far has been at the concentration level. This is a table at the concentration level. Now let's try to write the table for the P level. In a neutral solution, what would be the pH and the pOH? In a neutral solution, what would be the pH and the pOH?
7 and 7.
Because we know negative log of 10 to the negative 7 is 7. Okay, good. So this is something hopefully that you've heard in some of your other chemistry courses. Neutral is pH of 7. At room temperature or close to room temperature, neutral is pH of 7. Now actually, let's talk about another issue here then, a little detour that I forgot to mention. I have to take a little detour. There's something I forgot to mention. What does P of x mean?
Negative log of x.
Whatever x is. So when x gets bigger, what happens to the P of x? Does it get bigger or smaller?
When x gets bigger...
Does x move in the same direction as p of x or the opposite direction on the number line? If x is moving to the right on the number line, would p of x be moving to the right or left on the number line?
They would move in the same direction.
Same direction, so if one goes to the right, the other one would go to the right?
Oh, if it's negative log, no, it's opposite directions.
Like this?
Yes.
Because of the negative sign. So the more positive x becomes, the more negative the right-hand side is going to become. So these move in opposite directions. That's a very important principle here. So when you have a big x, does that give you a big or small p of x?
It gives you a small p of x.
So when the proton concentration goes up, what happens to the pH?
The pH goes down.
This is a very important idea that people have a hard time remembering because they both have H, but they move in opposite directions. The more protons there are, the slower the pH. That's a very important principle. I forgot to mention this earlier, but I should have. So when there's lots of hydroxide ions, what can you say about the pOH?
There's a lot of hydroxide ions, then the pOH goes down.
Again, they move in opposite directions. Good. Let's say we have an acidic solution. Does that mean the proton concentration is high or small?
The proton concentration is high.
Does that mean the pH is big or small?
The pH is small.
So notice acidic solution means two different things at the concentration level and at the P level. At the concentration level, acidic means a high concentration. But at the P level, acidic solutions mean a small pH. It's easy for people to start forgetting that. So how would we analyze a basic solution? Would that mean the proton concentration is high or low?
The concentration is low.
For protons, so what would that tell you about the pH?
pH is going to be high.
So what does that tell you about the pOH?
pOH is going to be low also. Well, it's going to be low. It's directly proportional to pOH.
The pOH will be small. When pH gets bigger, what happens to pOH? Hello again? I guess I have to turn my screen on again. That's annoying. I was asking you, when the pH gets bigger, what happens to the pOH?
When the pH is high, the pOH is low.
How do you know? Because pH plus pOH has to equal 14. So the bigger this is, the smaller this will be. Okay. Okay. All right, that was a little digression. I had forgotten to mention that before. So let's go back to our table here. What can you tell me about the pH for an acidic solution? What can we write here about the pH for an acidic solution?
The pH for an acidic solution would have a number less than 7.
And what can you say about the pOH?
In an acidic solution?
Yes.
It would be greater than 7.
We know in the neutral solution, pH is equal to 7. As things get more acidic, H plus goes up, so pH goes down. We were just reviewing that. And the opposite effect happens for pOH. So acidic solutions have pH less than 7. So let's try to work that out for a basic solution. What can you say about the pH for a basic solution?
pH is greater than 7 and the pOH is less than 7?
How do you know? Well, when it's neutral, the pH is 7. In the basic solution, there's a smaller number of protons, but a small H plus leads to a large pH. Okay, so now we finished this table here at the P level and at the concentration level. So we can compare the different types of solutions at those levels. Tell me when you have that in your notes.
Yes.
The big mistake people make is they assume that acidic means a high pH. They forget that pH is inversely related to acidity. So actually a low pH means acidic. Okay, let's try this problem.
So I can assume that the proton concentration is going to be less than 10 to the negative 7th.
That's a good point. So that would be a good estimation we could make, yes. So we could say that we know we're in a basic solution. Good. So now we have to continue with how we could calculate the exact answer, but that was a good start. So this problem is a little different than the ones I gave you before. This is a little harder than the earlier questions, but let's see if we can work out how to solve this. You made a good start. Okay, that's a very good idea.
Ten to the so H plus. Oh, that's H plus. That's the concentration. 10 to the negative 9.3.
Okay, so are you done? What's the answer?
Molar.
Okay, that's correct. However, that probably would not get us full credit because we don't usually report answers with fractional exponents. So although that's correct, the instructor probably would say you're not done yet. We don't usually give an answer with a fractional exponent. Now you're getting confused. We already know we started with the pH. The question is, how can you simplify 10 to the negative 9.3? Now you should use your calculator to get a more normal looking expression for 10 to the negative 9.3.
Times 10 to the negative 10. That's what I got from my calculator.
Okay, so what's our answer?
5.01 times 10 to the negative 10 molar.
Yeah, we need to put in those units. Okay, do you see why I said the earlier answer wouldn't be full credit? Because it's not in normal scientific notation. Scientific notation doesn't have weird exponents like 9.3. Now you have normal scientific notation with a normal looking exponent. And this matches your prediction of a small h plus, smaller than 10 to the negative 7. Okay, overall that was a good method. So I didn't quite show you how to do this type of problem before, so you had some good ideas here. One thing that you did that was very good is you realized that it would be better to write pH as negative log h plus. You wrote it as negative log h plus, and then you used the trick that we worked on last time of how well, the first thing you did was move the negative sign to the other side. That was actually a very good thing to do. You moved the negative sign to the other side, and then you used the trick that we've talked about how to get rid of the logarithm. Okay, but remember, we're not done with the answer until it's in normal scientific notation. So 10 to the negative 9.3 is not quite the answer. We have to put that into the calculator. Good. I'll go back to my screen. Okay, let's try this problem. Okay, we have to include the units to have a correct answer. Okay, so that was a review of the previous idea. Just to make sure we have this good in your notes, on your first line, why don't we put the -1 on the right-hand side in parentheses? Otherwise, it looks like we're subtracting 1. So it could be 5.7 parenthesis -1, just to show it's a multiplication for your notes. Okay, so that's a good method. Okay, I think we're making progress on that, so let's move on to the next aspect. Do you know what an acid is? What's the definition of an acid?
An acid is something that donates protons and accepts electrons.
Excellent. That's something we worked on a lot when we were working on organic chemistry. It's good that you remember that definition. An acid is a proton donor and an electron acceptor. People have a hard time remembering those. That's good that you remembered that. Probably in your biochemistry course, we're mainly going to focus on this part of the definition, proton donor. But it's still very useful to remember that that also means generally an electron acceptor. So we'll mainly be focusing on the proton aspect, but the electron aspect is good to remember as well. This is kind of what's called the Bronsted-Lowry definition, and this is what's called the Lewis definition of an acid. So that was correct. What's a base?
A base is something that accepts protons and donates electrons.
Okay. Again, something we worked on in organic chemistry. That's good that you remembered that. People tend to have a really hard time remembering these definitions, so that's good that those were still clear in your mind. We'll mainly focus on the proton aspect, but it is really good to keep the electron aspect in mind as well. So as we've talked about before, notice you can't just say that acids are donors. They don't donate everything. They donate protons, but they accept electrons. Okay, so to continue, what's the chemical equation for an acid? If I was going to write the chemical equation for an acid, the chemical equation for an acid looks like this. So in this case, rather than writing a specific acid, I've kind of written a general form of an acid. I think your textbook writes some things like this. HA here just stands for a general acid that has a proton to donate. So this is the general equation for acid ionization. This is an acid ionization equation. This is the equation for acid ionization. Okay, you have that down?
Hold on a second. Okay.
All right. Let's see. Do you remember what does AQ mean?
Aqueous.
That's what the word is, but do you remember what that means?
It's is it soluble in water?
It means dissolved in water. It means that this is a substance that has dissolved in water. Okay. So you can see how the acid here is donating a proton. So this is what we would call here an acid. A minus here has a name as well. A minus is the acid's conjugate base. This is the conjugate base of the HA. And actually, conjugate goes both ways. So this is the conjugate acid of the A minus. So the point is that these two are conjugates. Let's make sure we understand what that means. What was the proton definition of an acid again?
The proton definition of acid is it's a proton donor.
What do we call the acid after it's donated its proton?
An electron accepted.
But, no, that's not really what I was going for. What I was going for is after it's donated a proton, you call it the conjugate base.
Okay.
Do you see? The A minus is what the acid looks like after it's donated the proton. So what's the name for the acid before it donates the proton? Acid. But what's the name for the acid after it's donated the proton? Now it's the conjugate base of the acid. After the acid has donated a proton, it's not an acid anymore. After the acid has donated a proton, it's not an acid anymore. We need a new name for it. We can call it the conjugate base of the acid. Do you see this really is a base because this equation could be reversible? I'll write it like this to show that it could be reversible. If the equation went from right to left, this base would be accepting this proton. So this really is a base. So what do we call an acid after it has donated a proton?
The conjugate base.
Of the acid.
Or the conjugate. Yeah.
What's the proton definition of a base?
Proton definition of a base is a proton acceptor.
Good. What do we call the base after it's accepted the proton?
A conjugate acid.
That's right. Okay. So hopefully that clarifies that term. For example, have you ever seen this substance before? Is this an acid or a base?
It is an acid.
It's hydrochloric acid. What's the conjugate base of hydrochloric
Cl
acid?
minus.
That's right, because that's what it looks like after it's donated a proton. Is this an acid or a base?
That is an acid.
What's its conjugate base?
H2SO3 negative.
Like this?
It's HSO4 negative.
Because what's the definition of an acid?
A proton donor.
That's right, not an oxygen donor. So the acid is not going to donate an oxygen, it's going to donate a proton. And after it has, we call it, now it's the conjugate base. Now notice this is actually tricky because this acid has 2 protons. So this actually could act as an acid again. This could act as an acid again and donate another proton. So this compound is both acidic and basic. This compound is both acidic and basic, but in any case, it's the conjugate base of this acid. Okay, good. And that might not be obvious, but this compound can act like a base. What's its conjugate acid?
Is it NH2? It's a proton acceptor. So NH4 plus.
Like this?
Yes.
That was a good process. That was good how you worked it out. You started off on the wrong foot, but then you reminded yourself what the definition of a base is. What's the definition of a base?
Proton acceptor.
That's right. So you had to add a proton, not lose one. Now, this again could act like an acid. Theoretically, this could act like an acid, but I told you to treat it like a base. That's how it will act in the body. Physiologically, it'll act as a base. And also, what's the symbol for a proton?
Positive.
Good. So what's the symbol for a proton?
A plus sign, or H plus.
H plus. Not just plus, but H plus. So the important thing here is you recognized this is not just gaining a hydrogen, it's gaining a positive charge. I should have mentioned that up here as well. How did you know these were negative? Well, because we're not just losing an H, we're losing an H plus. If you start neutral and you lose an H plus, you become negative. If you start neutral and you gain an H plus, you become positive. So notice this is not the symbol for a proton. This is the symbol for a proton. Okay, good. So you worked that out. That's good. This can also act like a base. What's its conjugate acid?
NH3 plus.
Like this?
With the carbon chain?
Yeah, so it's still connected to the carbon chain. Okay, good. Do you know what role this plays in reactions?
That's an acid, so it's going to donate a proton.
Do you remember what the name of this type of functional group is?
That's a carboxylic acid.
We saw that in organic chemistry, so we know it's acidic. So let's write down its conjugate base.
It's going to be the same thing, but without the hydrogen and the negative next to the oxygen.
We got to put in that negative charge. Good. Okay. So we're going to be dealing a lot with conjugates in the course, so that's important to be clear about. Now, notice here, every acid is in equilibrium with its conjugate. There's always an equilibrium between the acid and its conjugate, or the base and its conjugate. Let's talk about strength. What's the definition of an acid?
An acid. An acid is a proton donor and electron acceptor.
Good. We'll focus on the proton aspect of that. What's a strong acid? What's the difference between a strong acid and a weak acid? You and I haven't talked about that. What's the difference between a strong and a weak acid?
Strong acid has a lower pH level. Has a lower pH level than 7.
Okay, that turns out not really to be correct. One reason it's not correct is that pH is not about the acid. pH is about the solution.
Is it its stability?
So who's more stable? The strong or the weak acid?
A strong acid is more stable.
Okay, that turns out to be a misunderstanding, so let's try to clarify that. So first of all, remind me again, what's the definition of an acid?
An acid is a proton donor.
But not all acids will donate all of their protons. Some acids are more eager to donate protons than others. So what I was going for is a strong acid is more eager to donate protons. A weak acid is less eager to donate protons. Strong acids are more eager to donate protons, and weak acids are less eager. Now, one thing that's confusing here is that the terms strong and weak can be used absolutely or relatively. They can be used absolutely or relatively. For example, if I say one acid is stronger than another, that's relative. If I say one acid is stronger than another, that's relative. What does it mean if one acid is stronger than another?
Oh, one acid has a higher tendency to donate its protons than another.
That's right. What about, though, if I just say this is a strong acid? That would be using the term in the absolute sense. What does it mean to say something is strong in the absolute sense? It means that it tends to donate all of its protons. In the absolute sense, a strong acid donates all of its protons, and a weak acid donates only a fraction of its protons. These two terms are commonly used. Strong acid donates almost all of its protons when it's in water, and weak acids donate only a small fraction of their protons in water. Now, there's one more term that's not an official term in your textbook, but I think we need to kind of make it up. Another term that's not official, but we need to understand this, I'll just make up a term and call some acids are super weak. It's not an official term, but it should be. A super weak acid donates, actually, maybe we don't need that. Maybe we don't need that. Okay. So what do you think a strong base is?
A strong base is something that accepts all the protons.
A strong base is something that ionizes completely. A strong base is something that where every molecule will accept a proton. What would be a weak base?
Something that doesn't accept all the protons.
So only a fraction of the molecules would accept protons. And now I have to make up a term that's not official, but kind of should be. There's also super weak bases. Super weak bases accept almost no protons. They're theoretically bases, but in practice, they accept almost no protons. Almost none. Of the molecules except protons. Okay, so tell me when you have that down.
Okay.
Now,
You don't need to know about super weak acids, right?
yeah, that's not going to come up. Okay, so we don't need the category of a super weak acid. That won't come up in your course. So if an acid is strong, is that going to make its conjugate strong or weak? If an acid is strong, will that make its conjugate strong or weak? Well, let's try to figure it out in terms of this equilibrium up here. Let's suppose that this was a strong acid in absolute terms. If it's a strong acid, does that mean the equilibrium here lies far to the right, far to the left, or in the middle?
Far to the left.
Like this?
If it's a strong acid, the equilibrium.
Will this reaction go far forward, or will it go far reverse, or will the equilibrium lie in the middle?
Oh, far forward.
Like this?
Yes.
Because when the reaction is done, will be mainly on the right or the left side?
On the right side.
Because almost all of these are going to donate their protons. There's going to be almost no HAs left. If this is a strong acid, we're going to be all the way far to the right. But do you see, what does that tell you about the conjugate base? If this equilibrium lies far to the right, does that mean that the conjugate base here, are these conjugate bases going to be picking up lots of protons or very rarely picking up protons to move the reaction to the left?
To move it to the left, it's going to be picking up protons.
Let me try to clarify what I'm saying. What I'm saying is, since the reaction lies far forward, are we going to have, which reaction is going to be occurring here? The forward reaction, the reverse reaction, or some of both?
The forward reaction.
Almost none of the reverse reaction, right? If the reverse reaction was happening, then this couldn't really be a strong acid because it wouldn't really be getting rid of all of its protons. Does that make sense so far?
Yes.
So what does that tell us about this conjugate base? Is it strong or weak?
Weak.
In fact, would you agree it's super weak?
Yes.
Almost none of these molecules are going to be accepting protons because that would be the reverse reaction. You told me the reaction was going all the way forward, not in reverse. So what we just saw here, we can draw a line. Strong acids have super weak conjugate bases. Strong acids have super weak conjugate bases. Okay. Now, what happens as this acid gets less and less strong? As this acid gets less and less strong, would you agree we get more and more of the reverse reaction? So as this becomes less strong, now we're getting more of the reverse reaction. So what's happening to the strength of the conjugate base? Is the conjugate base getting stronger or weaker?
As the strength of the acid decreases, the conjugate base strength increases.
Can you see that from the equation? Because now the reverse reaction is happening more. The stronger the conjugate base is, the more of the reverse reaction we're going to get. So what we're seeing here is as the acid gets weaker, the conjugate base gets stronger. These terms are here used in a relative sense. The weaker the acid, the stronger the conjugate base. That doesn't mean the conjugate base is strong in the absolute sense. That doesn't mean the conjugate base is accepting 100% of the protons. We're just saying in a relative sense, as the acid gets weaker, the conjugate base gets stronger. So suppose we've gotten to the point where this is a weak acid in the relative sense. I mean in the absolute sense. If this is a weak acid in the relative sense, that means a fraction of its protons are going to be donated. Well, that means now that we kind of basically have an equilibrium reaction that's going both ways. This is a weak acid, so that means a fraction of these are going to turn into the A minus, and a fraction are going to retain the H. A weak acid donates a fraction of its protons. So some fraction of this is going to donate a proton, and some fraction is going to stay as the HA. So we could write it as kind of equilibrium like this. So do you see that that means that the A minus now, the conjugate, would also be, in the absolute sense, a weak base? Because some fraction of the A minuses are going to pick up a proton and move to the left, and some are going to stay on the right. My point is that a weak acid in the absolute sense has a conjugate that's a weak base.
Okay.
Does that make any sense?
A weak acid has a conjugate of a weak base.
Because if the weak acid is if you have a weak acid, that means only a fraction are donating protons. Well, that means that some fraction of the acid is donating protons and some fraction is staying on the left. That means that the A minus has to be similar. Only a fraction are accepting protons to move to the left and a fraction are staying on the right. If the base was a strong base, then the reaction would look like this. If the A minus was a strong base, it would look like this, and then the HA couldn't be donating any protons.
But if you have a weak acid to begin with, you would never have a strong base, right?
If you have a weak acid, its conjugate is also a weak base. The conjugate of a weak acid is a weak base. I think that's what you just said. So what we've seen is that the conjugate of a strong acid is a super weak base. The conjugate of a weak acid is a weak base. The conjugate of a strong base would be a super weak acid, but we don't need to go through that because that's not going to come up in your course. So the point I'm making is that if something is a weak acid in absolute terms, because only a fraction only a fraction are donating protons, then its conjugate is a weak base. Also, that doesn't contradict this point, which is about relative terms. The weaker the acid is in relative terms, the stronger the base is in relative terms. When you make the acid weaker, you make the base stronger in relative terms. But that doesn't mean the base is strong in absolute terms. It's probably still only going to be accepting a fraction of the protons. So here's the 2 points I was trying to make. Tell me if this is making any sense, these two ideas.
Okay.
Is this making any sense?
Yes.
All right, I hope so. So the point I'm trying to make here is the weaker the acid, the stronger the conjugate base. But that doesn't mean that the conjugate base is strong in absolute terms. Weak acids in absolute terms still have weak conjugate bases in absolute terms. They're each only reacting a fraction of the time. It's just that as you make the acid weaker and weaker, the base gets stronger and stronger in relative terms. Well, hopefully this will clarify as we go along. So to continue, what is the acid ionization equation again?
It's The concentration of proton.
Let me repeat my question. I was asking you what's the acid ionization equation?
Oh, it's the
chemical equation for acid ionization.
HA aqueous, and then the equilibrium arrow to the left and right, and then we have the proton aqueous plus the acid with a negative charge aqueous.
The conjugate base, actually.
Oh, yeah, the conjugate base.
Okay, so this is the chemical equation for acid ionization. So next, it would be nice to come up with a mathematical equation for acid ionization. Well, this is a reaction that could be going to equilibrium. So the equilibrium constant for this is called the Ka. The Ka is the equilibrium constant for acid ionization. So what would be the mathematical equation here for acid ionization? Now I think you might have forgotten maybe from chemistry how to deal with equilibrium constants, but what you learn in your chemistry course is that you write the products on the top, you write the starting materials on the bottom, and that's equal to the equilibrium constant. So this would be the mathematical equation for acid ionization. You have that down?
Yes.
Now, this might look a little bit different from our Kw equation. The Kw doesn't seem to have a denominator. Why does this equation not have a denominator? Well, I briefly mentioned that to you last time. It's because pure liquids and pure solids are not included in equilibrium expressions. The equation for water has a pure liquid on the left. So the rule is you leave the liquid out, and there's no denominator here. But when we're dealing with an acid, it has something that's in aqueous phase on both sides. So now there is a denominator. The equilibrium constant, suppose the equilibrium constant was big. What would that tell you about the reaction? If the equilibrium constant is big, why would that happen? Would that happen if the equilibrium has lots of products or few products?
That would happen if it had few products.
How are you figuring that out? Are you using this equation to figure that out? So where are the products here on the top or the bottom of the fraction?
Bottom.
Take your time.
Oh, the top.
Yeah.
So it should be big.
So if this is big, that would happen because the fraction has a big top. So if the K is big, that must be because there's lots of products in equilibrium. If the Ka is small, what does that mean?
That means there's less products in equilibrium here.
So that means that the equilibrium, so when the Ka is big, does equilibrium lie far forward or far reverse?
Reverse.
That would give you lots of products?
To get for products it would be Forward.
All right, it looks like we're not understanding this, but that last answer was correct. But okay, so that should be pretty straightforward. When the Ka is big, that means there's lots of products in equilibrium. So does that mean the equilibrium is far forward or far reverse?
Far forward.
So would that correspond to a strong acid or a weak acid?
Strong acid.
Right. In relative terms. And when the Ka is small, would that be a relatively stronger or weaker acid?
Weaker.
Because it's weaker, we're not getting as many products here. Are stronger acids more, if something's a stronger acid, does that mean it's more reactive or less reactive?
It's more reactive.
Right. Is a stronger acid more stable or less stable?
Less stable.
Okay, that's right. Now, let's say that we have an absolutely, so in general, the stronger the acid, the bigger the Ka, and the weaker the acid, the smaller the Ka. Now, let's say you have an absolutely strong acid. What's the definition of an absolutely strong acid?
Something that donates 100% of its hydrogens.
So notice that for that case, the Ka would kind of be undefined. Because for an absolutely strong acid, what would go on the bottom here?
Would it be H plus and then H?
Let me help you with that. So these are the concentrations in equilibrium.
Mm-hmm.
So if you have an absolutely strong acid, how much HA is there going to be in equilibrium?
If you have a really strong acid in equilibrium, you're gonna have a lot.
No, we're not understanding that. If you have a really strong acid, does that mean the reaction is going far forward or far reverse or somewhere in the middle?
Far forward.
So how much of the starting material will be left?
None.
Yeah, I don't think that was your earlier answer. So if you have a really strong acid, how much of HA is left when the reaction is over?
None of it.
So what would go on the bottom here?
0.
So do you see why I was saying Ka is not really a useful concept for an absolutely strong acid? Because remember, you can't divide by 0. For an absolutely strong acid, Ka is undefined. So we only use Ka for weak acids. We only use the Ka for weak acids. The bigger the Ka is, the stronger the acid in a relative sense, but it would still be weak in an absolute sense. It's probably a good idea in your biochemistry course to memorize a few strong acids and strong bases. Do you remember any strong acids and strong bases from OChem?
You have H2SO4, HCl, HBr, HF.
HF is actually not a strong acid. HI is.
HIO.
Remember any strong bases?
NaOH.
These are the two that I wanted to mention. So what's the Ka for H2SO4? What's the Ka for H2SO4?
I don't know.
Well, remember H2SO4 is a strong acid, right?
Mm-hmm.
Do you remember that just a moment ago we were discussing what the Ka is for strong acids?
The Ka for strong.
Do you remember we were talking about how it's undefined?
Oh, I thought that was absolutely strong acids.
That's right. I guess I'm not being clear. This is a list of absolutely strong acids.
Okay.
These are a list of acids that are, these are acids that are strong in the absolute sense. That means they donate almost all of their protons. So what's the Ka for H2SO4?
Undefined.
Okay. Anything that's not in this list, these lists, is probably going to be weak. Things that are not in these lists are probably going to be weak. But one way you can tell if something is strong or weak, if the problem gives you the Ka, is it a strong or a weak acid?
It's a weak acid.
Because a strong acid wouldn't have a Ka. Okay. Okay, so let's move on now to some quantitative problems. Let's see how to solve these types of quantitative problems here. So here we have one problem. Now, a good place to start here then is by writing the acid ionization equation. So what would be the acid ionization equation in this case?
The acid ionization.
I'll help you with that. So this would be, here's the acid. What's the definition of an acid?
Proton donor.
So what goes on the right side of this equation?
H plus. And plus Cl minus.
This is what I mean by the acid ionization equation. Do you see how that's a logical name? Because the acid is ionizing here. Not to be confused with the water autoionization equation. Now it helps for these types of reactions. Do we expect this reaction to go to equilibrium or to completion?
I expect it to go to completion.
How do you know?
Because it's an absolutely strong acid.
That's right. How do you know it's a strong acid? Well, first of all, we just memorized it, but also there's a clue because I didn't tell you the Ka. Since I didn't tell you the Ka, that's a clue this is a strong acid. So it helps for this type of problem to make an initial change end table. This is a technique from general chemistry that's going to be still useful to us. An initial change end table. What's the initial concentration of HCl? And
I'm sorry, say that again.
what's going to be the initial concentration of the HCl before it has started to ionize? Well, that's where we use this number here. This number should be interpreted as the original concentration of the HCl. What's the original concentration of the products? Well, since the original concentration is the concentration before the reaction has occurred, these would start at 0 because the reaction hasn't had a chance to occur yet.
Okay.
Now, is this number going to go up or down during the reaction? Is the change going to be a plus or a minus?
One second, I have to rewrite this. What was that again?
Is this change going to be a plus or a minus? Is this number going to go up or down during the reaction?
It's going to go down.
Because we're using up the starting material. So should this change be a plus or a minus?
Minus.
How about this change?
That's going to be minus.
Or are we going to be creating or using up H plus during the reaction?
Using up.
I'm not sure why you said that.
Well, why would we be creating?
Because it's a product.
Okay, yeah, so then plus.
Right, I guess we're not quite understanding what's happening here. So what's happening is that we start with the HCl, and the HCl is going to be turning into H plus Cl minus. Well, once we understand it, it should be obvious that we're going to be getting more and more protons as the reaction goes forward. That's the way chemical reactions work. We use up the starting material, and we create the products. So are we going to be getting more or fewer protons as the reaction goes forward?
We're using plus more protons.
That's right. After all, that's what an acid is. It's a proton donor. It's donating protons to the solution. And are we going to be getting more or fewer chlorides?
Fewer chlorides.
So you're saying this will be a minus?
No,
I guess we're really confused here. As this reaction goes forward, we're going to be producing the products. That's the way a chemical reaction works. A chemical reaction uses up the starting material and creates the products. When we started, we had all of it was HCl, and we didn't have either of these products yet. So there's no way they could go down because they started at 0. Do you understand why I wrote zeros in the first row here for these two? Do you see where these zeros came from?
The zeros were because you used up all of it?
No, I guess we're really not understanding. Do you understand what I mean by the initial row? The initial row is what our concentrations are before the reaction has happened. So here's a reaction that's going to happen. The HCl is going to donate protons and turn into H plus and Cl minus. This row shows the concentrations before the reaction has happened. This row is going to show how things change during the reaction. And this row is going to show what the concentrations are when the reaction is finished. This is the row before the reaction has occurred. This is showing the changes during the reaction. And this row is going to show what the concentrations will be when the reaction is finished.
Okay.
Do you understand the idea of starting materials and products? What's the starting material for this reaction?
Hydrochloric acid.
So do you understand that before the reaction has occurred, all we have is starting material, and we don't have any products yet, because the reaction hasn't occurred yet. That's why these are zeros. It's not because they've been used up, it's because they haven't been made yet. This row is the row that's showing us what things look like before the reaction is. Maybe instead of calling this initial, maybe I should call it before. This is the before, and this is the after row. Before the reaction has occurred, all we have is starting materials, and we don't have any products. Now, during the reaction, are we going to be getting more or fewer starting materials?
We're going to be given more.
Starting materials?
We're going to have
during the reaction. During the reaction, is the amount of starting materials going to increase or decrease?
Decrease.
So should this change be positive or negative?
Negative.
During the reaction, is the amount of product going to be increasing or decreasing?
Increasing.
So should this change be positive or negative?
Positive.
And how about this change?
Positive also.
Okay. Those were not the answers we were giving before, so I don't think we were really picturing what was happening here. Okay, now how much of the HCl are we going to use up in this reaction? What number do we write here? All of it. How do you know all of it? Because this is a strong acid. So what number goes here?
0.
The change will be 0?
If we're going to use up all of it.
So don't confuse the change and the after. What I'm asking you about is what the change is going to be. What's going to be the change in the hydrochloric acid concentration?
It's going to be smaller.
No, we're not understanding. How much of the HCl are we going to use up?
All of it.
And how much is all of it?
0.083.
So doesn't that mean that's the number I should put here?
Yes.
But that's not what you were saying a second ago. This is the change. This is how much it's going to change by. It's going to change by negative 0.083. I guess maybe you don't have any experience with these before change after tables. Or this is a tool from general chemistry. It might have been a while. once we see it, hopefully it'll make good sense. We don't want to confuse the before, the change, and the after. All right, now all of the stoichiometric coefficients here are 1s. If 1 mole of HCl ionized, that would produce 1 mole of proton and 1 mole of chloride. If 2 moles of HCl ionized, that would give us 2 moles of protons and 2 moles of chloride. In this case, how much of the HCl is ionizing? 0.083 moles. So how much H plus is that going to create? What's going to be the change in the H plus?
Is it 0?
No change at all? We're not going to make any H plus?
I don't know what number to put there, though.
Well, if I ionized 1 mole of HCl, how much H plus would that make?
0.083.
From 1 mole? So again, if 1 mole of HCl ionized, how much H plus would that make? I guess these equations are just very unfamiliar to us. So what I was trying to say is, does it make sense to you that if you ionized one of these, you would get one of these? Every one of these HCl's makes 1 H plus. From one of these, you get 1 H plus.
Right.
All right? So if I ionize 2 of these, I would get 2 H pluses.
Okay.
All right? How about if we ionized 3 of these? How many H pluses would we get?
3.
Now, how much are we actually ionizing? How much of this is actually going through the reaction? Well, this much. This much is how much is actually going through the reaction. 0.083 molar is how much is actually going through the reaction. So how many H pluses will that turn into?
I'm sorry, I couldn't hear you. Say that one more time.
We know how much HCl is actually going to go through this reaction. 0.083 molar. Because all of it is going to react because it's a strong acid. 0.083 molar of this is going to react. So how much H plus is that going to create?
1.
No. Okay, well, we're really not understanding this at all. I guess I'll just demonstrate it and hope that it'll make some more sense. So you said this number should be 1, but that's not correct. This number should be 0.083. Do you see why these two numbers here should be the same? However much of this is ionized, that's how much of this we're going to produce. However much of this is ionized, that's how much of this we're going to produce. Each molecule of this produces one of these H pluses. So by the same token, we're also going to produce that much of the chloride. So then what would our after amounts be? Well, we started with 0.083 molar of the HCl. We used up 0.83 molar of the HCl, so we're going to have 0 left. We started with no protons, and then we created 0.083 molar of protons. So how many protons do we end up with?
0.083 molar.
That's right. Do you see how that just follows very easily from the table? We started with this, we added this, so this is how much we end up with. And then in this column, we started with 0 chloride, and we produced 0.083 molar of chloride. So how much would we end up with?
0.083 molar.
The table is supposed to make it easy to see that answer here. Okay. So once we understand this, this should be very straightforward. This is a strong acid, so it's going to completely ionize. All 0.083 molar is going to turn into protons. Once we understand it, the table is telling us a very, very simple story. It's just telling us that we start with this amount of HCl and it all turns into protons and chloride. None of the HCl was left over. Once we understand that, the table is very simple. In fact, the table is so simple that you might think you could do the problem without the table. The reason why we need the table is because there's going to be other problems that are not this simple. We're going to need the table to deal with all the variety of different types of problems. In this case, this analysis is so simple, you should almost be able to do it in your head without the table. We know this is a strong acid, so after the reaction is over, there won't be any acid left, and it will have completely turned into protons. Okay, well, we've been struggling with this for a while. Do you remember what the question was? What's the question?
Find the pH.
So now we're ready to do that. what's the definition of pH?
It's the negative log of the concentration of hydrogen ion.
Okay, but now we know when this reaction is over, what will be the concentration of protons?
0.083 molar.
So we take this number, concentration of protons after the reaction is over, and we plug it in here. Okay, now what?
Now calculate.
Okay, go ahead and tell me what you get.
.08.
So we have the pH here is 1.08, and now we're done with the problem. We spent a lot of time kind of talking on this. We had a lot of confusion, but now we're done with the problem. I spent a long time kind of talking about this because I felt like we were getting confused, but you can see it's not that complicated a problem. Here's the whole solution here on the page. Once we understand how to do this problem, it's not that complicated. We're just having some confusion setting this up. So the question told us that we have this solution of HCl, and it was asking us to find the pH. Now, what's the definition of pH? It's the negative log of the proton concentration. So logically, what we needed was this number. In order to solve the problem, we needed this number. We needed to know what's going to be the proton concentration after the reaction is over. Because when they say the pH, they don't mean the initial pH. They mean the pH after this has had a chance to ionize. When they say find the pH, they mean find the pH after the acid has a chance to donate its protons. Before the acid had a chance to donate any protons, the pH, the H plus concentration would be nothing. But after it's had a chance to donate protons, we can use this number to find the pH. So the key to solving these types of problems, this is what most of the problems in the review problems you were given were. You sent me a bunch of review problems from your course. They were mostly about finding the pH. So here's our general method for that. The general method is figure out how many protons there will be after the reaction was over. Like I say, I guess I wasn't explaining this very clearly because we had a lot of trouble with it. But the basic idea is very simple. How much acid did we put in?
0.083 molar.
And how much of it is going to turn into protons?
0.083 molar.
That's right. So how many protons are we going to end up with?
0.083 molar.
So that's all we did. We just put that number in for the number of protons, and we found its negative log to find the pH. That's all we were trying to say with this table. We started with no protons. All of the acid turned into protons, and so that's the number we used to calculate the pH. If it's so simple, why were we trying to struggle through the table? It's because there's a bunch of other problems in the review set that are different than this. You can't solve them all the same way. Each problem is different, so we really need to understand this table so we can adapt to the different types of problems. But this particular problem is straightforward once we see how to solve it. Okay, so the thing that makes these acid-base problems difficult is the problems are not difficult, but there's many cases. There's many cases that are all different from each other. Which case is this? So did we start with an acid or a base?
We start with an acid.
Strong or weak?
Strong.
So this is an example of a strong acid. Do you have that handout that I sent you last time?
Yes, I do. Okay.
You have that in front of you?
Yes.
All right, so you can see that that handout has the bad news. The bad news is there's many different cases for these types of problems, like I was just saying. So the handout doesn't tell you how to do the problems. It just summarizes the types of problems. There's many types of problems. You could have a problem with water, with a strong acid, with a strong base, with a weak acid, with a weak base, with a weak conjugate acid and a weak conjugate base. Then you could have much more complicated problems. The bad news is that the review problems that you sent me, they don't cover all of these, but they cover a lot of the stuff from this page. There's lots of different types of problems in that short set of review problems. So what have we covered so far? Well, we went over, I think we have kind of gone over how to find the pH for pure water. What is the pH in pure water?
The pH in pure water is 7.
That's right. We know that because what's the H plus concentration in pure water?
The H plus concentration in pure water is 10 to the negative 7.
So the pH is 7. All right, so last time we kind of covered, so we have the pure water case down. And we just covered the strong acid case. We just reviewed how to, so you might want to make a note that in today's tutoring we went over how to find the pH with a strong acid. So a few of the problems that you sent me are about this case. A couple of the problems you sent me are about this case of a strong acid. So now we know how to find the pH where there's a strong acid, although we've only done one example so far. But here's an example of how to find the pH when you have a strong acid. The bad news is there's many other cases, and they're all slightly different from each other. So it's kind of a time-consuming topic to cover. So anyway, we've covered the first 2 cases, and you should make a note that here in your notes you have an example of how to do the strong acid type. Also, you can see I have this coded with my videos, so you can kind of, this tells you which videos to look at to learn how to do each of these various cases. So that we've covered the strong acid case. And then the review problems cover a bunch of the remaining cases, like strong base, weak acid, and weak conjugate acid, and weak conjugate base, and even some more. So anyway, this is what we've had time to get to so far. One thing I should say is if you look to see how your instructor is doing these or how the textbook is doing these, they probably won't do it like this. Your instructor, your TA, probably won't use these before, change, after tables. But that doesn't mean that these tables are not important. It's just because your instructor or your TA or the textbook is probably doing this table in their head. The instructors generally do these tables in their head, but a beginner really has to do the table on paper. Otherwise, you can't see the difference between all the different cases. So we had some trouble understanding how the table worked here today, but you really do need these tables to understand the methods for doing these types of problems. Hopefully now that I've shown you the table for this case is making some sense. This was challenging because the biochemistry class goes over this very quickly because it's supposed to be a review from general chemistry. Unfortunately, a lot of people never really quite learned this or don't remember it from their general chemistry classes. So your instructor is going over the acid-base material very quickly, whereas in a chemistry class it would take a couple weeks to cover all these different cases.